Okay, hopefully you're back. Sorry about that. It took a little longer than I thought it would. Of course, the computer decided, oh, good, we'll just throw an update in as well. So hopefully this will be a little bit better. Thank you for hanging in there. So we're talking about oxidation states and again, ways to assign oxidation states. So just to kind of reiterate what we were talking about there before we stopped, again, you want to a lot of times start with oxygen is a really good place to start with, and then kind of work your way to the other guys. If you have sort of three guys together, that's a really good place to start. Go to the right, go to the left, and kind of save the one for the middle at the end. So why don't we take here a moment, and I want you to assign the oxidation states of each of these things, of each of these guys here. That seems a little bit better. Okay. And we'll talk about the oxidation numbers of each of these guys. So for each of the elements here, assign the oxidation states. So again, those coming in, we're just working on this example here. So give it a go. And oops, don't change it. There you go. And then we'll talk about it obviously in a sec. All right, so let's take a look and see how we're doing. So here we have Li2O. So we start with the oxygen, which is going to be -2. And lithium here is going to be +1 like it normally is. And there's two of them, which obviously will give us 0. So lithiums would be +1. Oxygen will be -2. Again, you do want to include the charge there when you are writing the oxidation numbers. PF3, again, fluorine will always be -1. There's three of them, gives you a -3. That means in this case, the phosphorus should be +3. And again, when you're asked for the oxidation state or number, it's not the grand total. It is the individual oxidation state on each of the elements. And if we look at HNO3, NO3 is -2. Oxygen is -2. There's three of them, gives you a -6. Hydrogen is +1 on the other side. In this particular case, it does add up to 0, all the numbers, since it's neutral. So to balance that out, the nitrogen would have to be +5 in that case. So hydrogen is +1, nitrogen is +5, oxygen is -2 in that case. And lastly, we have our dichromate, which is Cr2O72 minus. Here again, starting with the oxygen is -2. That gives you -14. In this case, it does need to equal -2. And there's two chromiums. So you could do like a little math problem if you like. And if you solve for x there, x is going to be +6 in this case. That gives us +12, and -14 gives us a -2 left over. And again, here, chromium would have a +6 oxidation state. Oxygen would have a -2. Any questions on how to assign oxidation numbers? So again, important, people oftentimes screw up on the, we're just going to give the grand total of everything. So again, for something like oxygen, they would put minus 14, which again is not the correct oxidation state. Again, it's just minus 2. You just want to give it for the individual guy by itself. And then the other thing that people kind of screw up on is they don't put the charges, the minuses and the pluses. So always when sort of identifying oxidation states, even with things that are positive, you should still put the plus side to indicate that obviously you know that it's positive, and then it's not -2 or anything like that. Any questions on that there? So as I mentioned before, I know perhaps maybe some of you are familiar with balancing sort of redox reactions in acidic or basic conditions. But what we're going to talk here again is just to make sure everybody's on the same page and sort of the steps to follow when you have a little bit more of a complicated redox reaction that you need to balance in either acidic or basic conditions. So the first thing you want is the unbalanced equation, which would look something like this in this particular example. We could also look at this and sort of figure out what's going on. The oxidation state of our iron 2 over here should be iron 2 plus 2. Obviously, our iron 3 is plus 3. We just did this guy. Again, oxygen's minus 2 here. Chromium ends up being plus 6. Chromium over here ends up being plus 3. So again, if you follow sort of that little number line sort of approach, if we look at the iron, it started at plus 2, which would be over here, and ended at plus 3, which would be going in this direction, which means it's oxidation. While if you look at the chromium in this particular case, the chromium in this case is starting at plus 6, which would be down here, and ending at plus 3, which would be going in this direction. And again, in that direction, it is reduction. So in this particular example, the iron is being oxidized. And because the iron here is being oxidized, it is the reducing agent. While the dichromate over here is being reduced, which means the dichromate is the oxidizing agent in this case. So again, those guys are opposite of each other. So when you go to balance these redox reactions, really the first thing you want to do is kind of split it off into its 2 half reactions. So there's our 2 half reactions, and basically you're just going to pick the 2 guys that are basically the same guy on each side. So we got iron and iron, chromium and chromium, basically will stay together. So as we just saw there, the iron going through oxidation, and again, going to be our reducing agent, the iron 2, and the dichromate going through reduction, going to be our oxidizing agent. Then typically what you want to do is balance it like you normally would a normal equation by putting coefficients. And what we want to balance is everything other than oxygen and hydrogen. So we want to balance everything but oxygen and hydrogen. And in this case, we have 1 iron on the left, 1 on the right, so it's good. In the bottom case here, we have 2 chromiums on the left and only 1 on the right. So we would want to balance that chromium by just simply, like a normal reaction, putting a coefficient in front. So we'll put that 2 in front of the Cr3 to balance the chromium. Because really the overall goal here is to, when you're all done, have an equation that's balanced really in sort of 2 ways. Balance like a normal equation, like you have the same number of elements on each side. And secondly, you want it balanced in terms of charge. The charge on each side, the reactant side and the product side, does need to equal each other. It doesn't necessarily have to equal 0 on both sides, but it does have to equal the same sort of overall number. Once you do that, the next thing we're going to do is balance the oxygens. So after you balance everything but oxygen and hydrogen, we balance the oxygens. And the way we balance the oxygens is we add water to the mix. And we add water as a way of balancing the oxygens. So when you look at your half reactions, there may be one side that has more oxygen than the other. So to fix that, we're going to add water to the side that needs the oxygen. The consequence of adding water is every time you add a water, you're basically adding 2 hydrogens. So to fix that, to the opposite side that you add the water to, you should add 2 H pluses to balance out the hydrogen. So to balance out the hydrogen, we really use H plus, and you basically need to add 2 for every water you add. So basically one side will get the water, the other side will get a couple of hydrogens, H pluses. Again, that's going to balance out both the oxygen and the hydrogen. Also means that if for some reason you start with a half reaction that you have more hydrogen on one side than the other, you can just add the H plus in to balance it out as well. So in this case, before we started, we had 7 oxygens on the left, none on the right. So that is why we added 7 waters to the right-hand side. Because we added 7 waters, we're going to need to add 14 H pluses to the other side to balance out all those hydrogens that we added. So again, one side gets the water that needs the oxygen, the other side gets H pluses to balance out the hydrogens. In the case of the iron, there was no oxygen on either side, so we didn't have to worry about doing any of that for the iron part of it. Now you come to the part where you basically want to balance out the overall charge on each side. Now, before we add the electrons here in the top one, the overall charge on the left-hand side is +2. Overall charge on the right-hand side is +3. So the goal here is to balance it out to make it the same number on each side. Again, it doesn't have to be 0, but it does have to be the same number. And the only way we're going to do that is by adding negative electrons. So you need to add electrons to whichever side will help you in that. So in the case here, we just need 1 electron, and that's going to give us a -1, and overall a +2 on the right and a +2 on the left. So that's balanced. On the bottom guy, again, before we added the electrons, we have +14 here. This whole entire thing is -2, and that gives us a grand total of +12 on the left-hand side. This guy here is 2 times +3 is +6. This is 0. So that gave us a +6 overall here on the right-hand side. So that is why we needed to add the 6 electrons to the left-hand side. When we do, 6 electrons gives us a -6, and that now gives us a +6 over on the left and a +6 overall on the right-hand side. So we do want to add electrons to balance out the charge on each side of the half reaction. Again, the charge does not have to equal 0, but it does need to equal the same thing. We also can check to make sure we sort of are doing this correctly based on what we identified earlier. If you remember, this was our oxidation half reaction. And in an oxidation half reaction, electrons should always be on the product side. Well, this was our reduction half reaction, which means those electrons should be on the reactant side. So that is good. We added the electrons to the correct sides. Also, when you add electrons, as you should know, as we talked about, since one is losing and one is gaining, if for some reason you find yourself adding electrons to the same side, you are messing it up, yes? So electrons should always be added to opposite sides of those half reactions. And that's because ultimately what you're going to do is cancel out the electrons. And when you balance these things, you want to make sure that the electrons completely cancel out. And that also means that when we get to this step, we're ready to add these back together, but we need the same number of electrons in each half reaction. So top one has 1, bottom one has 6. So we need to multiply not just the electrons in the top one by 6, but the entire thing. So what we would do is take that top one and we would multiply everybody in the top equation by 6. That's going to give us the same number of electrons. And again, still keep everything balanced in terms of atoms and charges. At this point, once we got all of the electrons the same in both half reactions, we balanced everything in terms of elements. We're now finally ready to add these back together. And if we do that, we will see that the electrons, again, should cancel out completely. And then pretty much everybody on the left-hand side of the arrow stays on the left-hand side of the arrow. Everybody on the right-hand side of the arrow basically will stay on the right-hand side of the arrow. This equation that we see here should represent the balanced equation in acidic conditions. So this represents the balanced equation in acidic conditions. And if we just take a quick look, we got 14 hydrogens. 7 times 2 is 14 hydrogens. 2 CRs, 7 oxygens. 7 times 1 is 7 oxygens. 6 irons, 6 irons. So it's balanced like a normal reaction in terms of elements on both sides. Overall charge plus 14 on the left and minus 2 gives you a plus 12. And 6 times 2 is 12, so that's a plus 24 overall there if you add up the entire charge here on the left-hand side. Right-hand side, 6 times 3 is 18, and 2 times 3 is 6, so 18 and 6 is plus 24 on the right-hand side. So that is always what you're trying to achieve, is an equation that's balanced both ways, if you will. One way, same number of elements on each side, like a normal equation, and the overall charge on each side equals each other. So those are the steps to balance these redox reactions in acidic conditions. Now, if it was basic conditions, you essentially would do the exact same steps. And the easiest way probably is to just, even if you're balancing in basic conditions, you should just follow the same steps for acidic conditions. The difference, though, with basic conditions is when it's all done, what we're going to add is OH minus to both sides. And we're going to add OH minus that's equal to the amount of H plus that you have. So in the equation that we have above, if we were to balance this in basic conditions, we would look at it and go, on the left-hand side, I see there's 14 H pluses. That means I need to add 14 OH minuses, not to just one side, but to actually both sides. And what's going to happen when you do that is, on one side, you'll have 14 H pluses and 14 OH minuses. Those are going to make water. So to illustrate how we do that there, come here, go back this way. So if we wanted to do this guy in basic conditions, we would follow, again, all of the same steps as we just talked about. We would end up pretty much where we're at. And at this point, after we balance it in acidic conditions, this would tell us that we need to add 14 OH minuses to both sides. So you would do that. Everything here would be exactly the same. And again, on the other side as well. Now, as I mentioned, the side where you have the H plus and the OH minus, they are going to combine to make 14 waters. And you kind of combine 14 on this, leaves us plus everything. And if we start everything, this should be balanced both in element and charge. So let's take a look again just to verify. We have 14 hydrogen on the left, 14 on the right. We have 7 and 7 oxygens on the left, gives you 14, 14 on the right. 2 CRs on the left, 2 CRs on the right, and 6 irons on the left, 6 irons on the right. Overall charge, if we add up all the charge on the left-hand side, we have plus 12 and minus 2 is plus 10, I believe. And on the right-hand side, we have, what we got there, plus 18, and 6 is plus 24, less minus 14 is plus 10 as well. So it would be balanced. So this would represent the balance equation in basic conditions. So there's actually many ways you could kind of balance sort of these reactions or thought processes as you go through it. I personally perhaps think that this is the easier way, just to do everything acidic and kind of add the OH minus at the end. Some people will add the OH minus in the part right before you add the electrons, which you could absolutely do that as well. And that's another common way of doing these, is to sort of add the hydroxide before you add the electrons in each half reaction. You could do it that way as well. I say probably the only downside of doing it that way is you create a lot more stuff that needs to be canceled out earlier on. But if you could kind of keep track of everything, you could do it there, or just wait to the end and sort of do it. Also, in terms of adding the electrons, sometimes people like to go by the individual element and sort of how many electrons is gaining and losing, which you could do that if you understand correctly how that works, and take into account coefficients and what's happening there. I personally think also as well, when you add the electrons, it's just easier to look at the overall charge on the left and the overall charge on the right. And what I mean by that is you take something like CR 207 2 minus, right? So, we know individually, hey, that's +6, which means technically it lost 6 electrons and all that kind of stuff, right? And this guy's -2. But, you don't really need to, in a case like this, sort of look at each of the individual oxidation numbers, because really that's your grand total for everything that's going on in terms of all those individual elements. And if you could just look at the overall sort of change that's happening in terms of charge on the left and the right, and you'll be fine. And again, it just keeps it a little bit easier to do than sometimes maybe looking at each individual one and having to remember, oh, there's 2 chromiums in that case. I need to adjust and all that kind of stuff. Any questions on the steps here to balance a redox reactions in acidic or basic conditions? So after all that talking and delay, why don't you try one here? We want to balance this in basic conditions. So why don't you give it a go and see what you come up with, and or at least get started on it, and then we'll talk about it in a few minutes here. Okay, so let's kind of see how you're progressing. Again, even if you haven't finished it, let's take a look and see what we end up with here. All right. So again, the first thing you sort of want to do, as we talked about, is really just kind of split them off into the two things that are related to each other. So obviously, I minus and I2 are related to each other, and MnO4 minus and MnO2 would also be related to each other. And we want to look perhaps maybe at the oxidation states of each of these so we have an understanding of what is happening. Obviously, I minus would have an oxidation state of -1. I2 is in its natural state, so that's going to have an oxidation state of 0. Again, if you look at that number line, if you're not sure, the I minus is starting at -1, which would be over here, heading towards 0, which would be to the right. And again, things going to the right there, becoming more positive, is going through oxidation. So this would be our oxidation half reaction. While if we look at the Mn over here, again, the oxygen is -2, and that's going to give us -8. It has a -1 overcharge. So the Mn here is +7 on the left. Oxygen over here is -2. There's two of them, that's -4. And the Mn would be +4 in that case to balance it out. So for our Mn, it is starting at +4, which would be, where are we at there? There we go. +4 and +7. It's starting at +7. I'll learn to count here. Let me try that again. That's +7 and ending at +4. I'm like, wait a sec. And it's going in that direction. So that is reduction. Get a calculator, maybe. All right. And that would be our reduction half reaction. By the way, if you can figure out one of them, by default, the other one is what's happening in this particular case. That would also mean that our I minus here would be our reducing agent. This guy here would be our oxidizing agent. Any questions on, again, how to identify those things? All right, so now that we've sort of identified what's happening, and again, it's a good thing to do because it will kind of help you as you're going along to make sure you're sort of doing everything sort of correct. I'm just going to rewrite them here, kind of freshly work on it, hopefully. All right, so the next thing you want to do is balance everything but oxygen and hydrogen with coefficients. So we do need to put a 2 here for the iodine. In terms of here, we have 1 Mn and 1 Mn, so we don't necessarily need to add any coefficients to the bottom. Once we've done everybody that is oxygen and hydrogen, besides oxygen and hydrogen, then we're going to go to oxygen. There's no oxygen in the top one. There's 2 on the right, 4 on the left. Bottom guy needs 2 waters. And again, every time we add 1 water, we need to add 2 H pluses. So in this case, to balance it out, we would need 4 H pluses because, again, we added 2 waters over here. Now we have everything balanced, both the oxygen, the hydrogen, all of the other elements. So the next thing that we want to do is balance out the overall charge on each side. Overall charge on the left-hand side on top here where the I is 2 and -1 is -2. And overall charge on this side is 0, which means the right-hand side here will need the 2 electrons. And that is good because we saw this was our oxidation half reaction. So our electrons are on the right-hand side, and that's where they should always be. If we look at the overall charge on the bottom guy, we have +4 from the hydrogens and -1, just taking the overall charge there. That gets us a +3 situation and a 0 over here on the right-hand side. And that means that the bottom guy would need 3 electrons to the left. And that also is good because that is a reduction half reaction. Any questions on that so far? Now, once we have the electrons in there, we're ready to add them together. But again, before we could add them together, we do need to make sure that we have the same number of electrons on each side, and we don't. So the common number between 2 and 3 is 6, which means we technically need to multiply the top one by 3 and multiply the bottom one there by 2. And if we do that and sort of rewrite everybody here, we will end up with 6i minus goes to 3i2 and 6 electrons. Bottom guy will go 6. Oops, come back. Try that again. 6 electrons plus 8 H pluses plus 2 MnO4 minuses, 2 MnO2 and 4 waters. Taking everybody here together, we can now add them together. Our electrons are going to cancel in this case, and that's going to leave us 8 H pluses plus 2 MnO4 minus plus 6i minus. Again, everything on the left stays on the left. And on the right-hand side, 3i2s plus 2 MnO2 plus 4 waters. And if I did everything correctly, this would be the equation that would be balanced for acidic conditions. Any questions on that before we finish it up here? By the way, if we look at it just to verify that we didn't mess up anything up until this point, we have 8 hydrogens on the left, 8 on the right. We have 2 Mns on the left, 2 on the right, 8 oxygens on the left, 4 and 4 is 8 on the right, 6 I's on the left, and 6 I's on the right. Overall charge on the right-hand side is 0, it looks like. Overall charge over here, +8 and -8 is 0. So at this point, it would be balanced in acidic conditions. So what we're looking for at this point, though, is basic conditions. So what we want to do is we want to add OH minus to both sides. So what I'm going to do is try to find a fresh little spot there. So let's flip the page here. I think that should be empty. So what I'm going to do is just going to rewrite the one that we finished up on there. So we finished with, for acidic, 8 H pluses plus 2 MnO4 minus plus 6 iodide. Gives us 3i2 2 MnO2 and 4 waters. All right. So now what we want to do is we want to add OH minus to both sides because we want to balance this in basic conditions. And the amount of OH minus is equal to the H plus. So we would add 8 OH minuses to the left. We would also add 8 OH minuses to the right. These guys are going to combine to give us 8 waters plus 2 MnO4 minus plus 6 iodide, 3i2 plus 2 MnO2, 4 waters, and almost running out of screen here. 8 OH minuses. Just like usual, we will have to reduce down some of our waters, and that is going to get us 4 waters plus 2 MnO4 minus plus 6 iodides, 3 of these guys, couple of those, and 8 of those. And at this point, this should be the balanced equation in basic conditions. And again, if we look at it, it should be balanced both ways. We have 8 hydrogens on each side. We have 4 and 8 is 12 oxygens on each side. 8 and 4 is 12. 2 Mns, 6 Is. Overall charge on the left-hand side is -8, and we get that from basically -2 from this guy and -6 from that guy, and -8 on the right hand side. So we are balanced in both ways, which you should always get, both in terms of elements and overall charge. Any questions on those steps? All right, so what I think we're going to do today, since we had a little trouble here and all that good stuff, is we're going to take a break, and at 11:30 we will start lab at its normal time. And what I'm going to do is I'm just going to continue to lecture on here so we can get into some of the actual electrochemistry stuff just to keep us on pace. And the next experiment, which is actually it's redox reactions. I think after the lecture today in lab, where we get decent and far enough, should probably allow you to probably get started on that next experiment. And I'll probably post the next experiment the next day or so in case you want to get started on it, which would be technically the one that's scheduled for today, which I think is the redox experiment. So again, I just want to make sure I cover enough of this stuff so you can kind of get working on those experiments. So that's what we'll do for lecture. We'll do a little bit of lecturing on this stuff, and then afterwards, again, if you have questions on any of the experiments that's out there, like the titration one or something like that, you'll be more than happy to, for the rest of the lab part, sort of answer those questions. The due date again for the titration lab, as I moved it to next week, just to give you some extra time if you want. So it's officially due, I think, next Thursday, if I'm not mistaken. So that should give you some extra time to do that if you need. And there's a spot there for you to upload your report for that one. Again, a reminder that I know some of you are still working maybe through the buffer one, or then you haven't completed the buffer one. Again, the way it's set up there, I think you could still kind of finish it and submit it if you need to, even if it's late. And like I said last time, when I do grade it, I'll look at how late it is perhaps and make any appropriate adjustments. But if you still want, obviously some points better than none, if you want to turn it in, I think you should still be able to do that as well. Any questions on any of that stuff? All right, so about 11:30ish, come through the lab lecture meeting, and again, we're just going to continue lecturing on some of this stuff. We'll do maybe another example of this just to make sure, and then we'll get into some galvanic cells and some electrochemistry type stuff as well. Any questions? Okay, I'll see everybody in about 20 minutes or so.